All right, so now we're going to talk about in video 9, data handling and file registers. It's a very important part of ladder logic programming. We want to understand the different file types that are involved with the MicroLogix PLC. That would be the B, which are binary files, T, timers, and C, counters, etc., that you'll run into in RSLogix. And also we're going to cover data transfer and manipulation. The binary file starts at B3 within the MicroLogix 1000, and this is a picture of the data table right out of the processor. You got B3 colon 0 through B3 colon 10. Of course, you can increase the size of this, but each of these B3 0, B3 1, and so on, each is made up of 16 bits. So, for example, in the diagram here, you've got B3 colon 0 slash 0. That would be highlighting bit 0 of that binary word, B3 colon 0. But we'll get into using these more as we go in the code. The file type, it's known as binary, and the addressing format is B3 colon X slash Y. Let's go ahead and get a pointer going here. And then B3 is the binary file default. You can create more binary files, like you could have a B10, a B12, whatever, if you need more words than what you'll find within B3. But the X part of it, the B3 colon X, this X here represents a word number from 0 to 255. Now that does depend on the PLC model as far as how much you could get. The maximum that you would get in B3 would be 255 words. The Y at the end represents the bit number, and that's going to be 0 to 15 within each word. And the purpose of these really, it's just to store individual bits, either a 0 or a 1. And these are used in the programs for like things like internal relays, some flags or intermediate logic conditions. It works very similarly to relay contacts within ladder logic. And the big thing is that remember the binary files, the B3s, are internal relays. They're not real world outputs like the O addresses. And memory allocation wise, by default, B3 is the first available binary file in the PLC. And again, each word is 16 bits, so each word can store 16 on or off values. And the total number of available words really depends on the MicroLogix 1000 memory size, as I mentioned before. Now the usage in ladder logic, it's used for control logic, things like latching and interlocks, which we'll get into a lot more as we go through. There's some example instructions here that interact with binary files. There is the XIC, which is examine if closed, checks to see if a bit is 1, and it looks like this. You can see the address B3 colon 0 over it. It's basically a normally open contact. You also have the XIO, which is examine if open, checks to see if a bit is 0. And in this case, you can see it's highlighted. This is a normally closed contact, which by default passes power. And you have the output latch, OTL, which sets a bit to 1 until it gets unlatched. So you see the L inside of the coil represents it's an output latch bit. An output unlatched bit resets a bit to 0, and that has the letter U inside of the coil here. Then also we have move instructions where you can transfer an entire 16-bit word to another location. For example, in this move instruction, we're moving all 16 bits of B3 colon 0 into the destination B3 colon 1. Now, so example usage here would be like, say, turning on a light when a switch is pressed. And so, for example, here you've got I colon 0 forward slash 0, which could be the input from a switch, and you see it right here as a normally open. and then B3:00 could be an internal relay. So we need this to actually be turned on as well. This input would have to close, this contact would have to close, and then that would energize our coil here for O:0/0, which would be our output to the light. All right, so by this point we've covered timers and counters already, but what we're showing here is just an example of what the ladder logic would look like using those with inputs driving a timer and an input driving a counter. This is an up counter, and this would be a timer, an on timer, which is set for looks like 1,000 seconds. So the next thing we want to look at is data transfer and manipulation. Now, data manipulation in a MicroLogix 1000, uh, basically you've got various instructions here for moving, copying, and modifying data. The PLC operates primarily on words, 16-bit words. Some of the newer controllers, like the ControlLogix Compact Logic series, those work in double integer, 13-bit words. But in this PLC, it's all 16-bit based. And the one first instruction we want to look at here is the move instruction, which is represented by MOV. It moves a value from one location to another. And the syntax of that would be you move the source to the destination whenever this instruction is energized. So for this instruction, we're moving N7:0 to N7:1. So integer file 0 is being moved to integer file number 1. And again, the move instruction that works with integer files, those are the N's, timers, T's, counters, and also binary files. Another instruction that we've got here is the masked move, MVM. It moves data while applying a mask or like a bit filter. And so the mask basically determines which bits get transferred. So if there's a 1 in a particular bit location, it means the corresponding bit from the source will get passed on to the destination. If there's a 0 in the mask at that bit location, we will not transfer the bit from the corresponding source over to the destination. So in the example we've got here, the mask is FF hex. If you're familiar with FF hex, it basically means your lower 8 bits are all set to ones. So it means that only the lower 8 bits of N7:0 will actually get moved to N7:1. Now, if that's a little bit confusing to you, you may want to review number systems. We basically spend most of our lives working in the decimal system. We basically have got numbers, digits that go from 0 to 9 that represent all the numbers that we know. But there's also, binary, which is base 2. You've got octal, base 8, hexadecimals, base 16. There are other number systems out there. I don't want to get into a whole lot of detail with that. I've actually got another video on the channel that does talk about number systems if you're not familiar with how those work. But I wanted to just briefly cover the instruction here to explain what the masked move is about. And yeah, this is just showing an example here of if you have hex FF, that's the equivalent of decimal 255. And then octal is base 8, and then your binary here. I like to look at it in binary because, again, you can see there's 8 bits that are all 1. So if my mask is FF hex, that's the equivalent of binary 11111111. All these 8 bits being set to 1. So that means the low 8 bits of the source will get passed on to the destination. There's also a clear instruction, which is very useful. It just really resets a register or memory location to 0. In the example here, we're clearing the value in N7:0. We're just clearing it to 0. There's no need to move. I mean, you could do this with a move instruction. You could move 0 into N7:0, but you can just write it with a clear instruction. It does the same thing. All right, there's also another one. I haven't used this one a whole lot, but there are some uses for it, believe it or not. It's the swap bytes instruction. The is one that you can swap high and low bytes in a 16-bit word. Oh, that's actually useful when you're interfacing with Modbus or some external devices. Some devices actually you need to swap the order of bits in a word. Modbus is actually just a communications protocol, which I won't get into here, but that is kind of a useful instruction. The one that I'm showing here is the XOR in the diagram. You have XOR and OR, which do logical operations. XOR is a bitwise exclusive OR instruction. You've got, you got some other ones here. You got the and the or, which basically are just Boolean logical type operators that you have access to in the PLC. I won't go into too much detail on those at the moment, but I wanted to mention something about file handling within the MicroLogix 1000. It, the MicroLogix 1000 stores and organizes data into different file types, which we've kind of gone through these a little bit already, but I wanted to go through them again. You have the inputs, which represent physical inputs from devices like switches, push buttons, and the address example here, I:0/0, which is a bit. I:0 would be a word representation representing all 16 bits. Physical outputs to devices like lights, solenoids, motors, etc. O:0/1 is a bit. O:0 would be a word. You have the binary files, which are internal bit storage for flags and other logic. Here's an example of a bit, B3:0/2. So bit 2 of B3:0. Timers store timer values and statuses. Your presets, your accumulator values, your done bits for timers. T4:0.pre represents the preset of a timer. That might be equal to something like 500, which would mean maybe you want to count up to 500 seconds, or time it to 500 seconds, not count. Excuse me. C counter stores counter values and statuses. C5:0.acc would be the accumulated value within a counter. You got the integer files like N7:0, and then float, which basically F8:0. So if you want to have mathematics where you're actually dealing in not just strictly integers, but you want to have like floating point values like 8.5, things like that, then you want to be using the floating registers. So yeah, for file access and manipulation, the addressing format again to keep in mind is the file :element/bit. An example is B3:2/5, and what that means, it means bit 5 in word 2 of the binary file B3. So you want to keep that in mind. And word level manipulation, say if I had a move instruction, moving N7:0 to N7:1, that's moving an entire whole word of 16 bits. And then with bit level manipulation, you have the output latch, which an output latch for B3:0/1, it latches bit 1 of B3:0. So timers and counters within data manipulation. Timers and counters have presets, they have accumulators, and status values that can all be manipulated. Here we have an example of a timer, T4:0. The time base is 1, which means it's going to time in increments of 1 second. The preset is 10, which means that this timer will count up to 10 seconds before it turns on the done bit. And again, the accumulated value is in T4:0.ACC. The done bit, it turns on, it becomes a 1 when the timer's finished. It'll do that once the timer has reached 10 seconds. Now, here's a counter example. This is an up counter. Again, this counter is set to count up to 10 before it fires its done bit, which would be C5:0.DN. The accumulated count, we know where it happens to be at the moment, as it's counting, that's stored in C5:0.ACC. So pretty straightforward. Now we talk a little bit here about data storage and file management. Um, the MicroLogix 1000 doesn't have a traditional file system like a PC would, but data files are stored in non-volatile memory. It's a double EEPROM, and for the data retention, the program and data files will remain stored even after a power cycle. I will say I had an issue years ago. I think it was an old Allen-Bradley PLC 2 where they did not have an EEPROM module. And back in those days, a lot of the processors were battery backed, and the battery actually failed and they lost the program. And unfortunately, nobody had a recent printout or a saved copy of it. So it was quite a bit of work to get that reprogrammed. Um, but uh, but for memory backup, you want to use RSLogix Micro Starter Lite. Allows you to upload and download programs, so there's really no excuse to not have a saved copy of the program if you have the software. You always want to make sure you've got a copy of the most recent files available. And here's just a real brief example of manipulating data within a PLC program. Let's say that you need to read an input sensor, which would be I:0/0. You want to store its bit in the binary file bit, bit 0 of B3:0, and then you want to use that binary value to activate an output, which would be bit 0 of O:0. So this would be two rungs of ladder logic to do that. You've got an input sensor here. This would be going to the binary file bit here in the coil, which when this is energized, that means this normally open contact would close, and then it would fire this output, energize the output. So you're checking to see if the input's on, store the on state in a binary file bit, and then use that stored value to turn on an output. So pretty basic. So, some practical use cases here. For bitwise control, you want to use B3 bits to create logic interlocks. For math operations, I recommend, if you're using integers, use the N7 addresses. Timers and counters are something you'd be looking at to delay operations or counting how many times something happens. Data logging, you could store those values in N7 or F8 addresses for later reference.